We can identify non-homogeneous linear systems by the presence of the independent variable t explicit in the system. Here we have x prime equals the 2 by 2 matrix 1, negative 4, 4, 1 times x plus the column vector 4t plus 9e to the 6t negative t plus e to the 6t. This column vector that contains functions of t is represented f of t in the symbolic equation for the system. We're going to start with the method of undetermined coefficients, but it's really of particularly limited use in solving systems of differential equations. I'll get to that later, but step one is to solve the homogeneous system x prime is equal to ax using the coefficient matrix in the non-homogeneous system. In order to do that, we find the determinant of 1 minus lambda, negative 4, 4, 1 minus lambda, and set it equal to 0. This is going to give lambda minus 1, the quantity squared, is equal to negative 16. And so lambda is equal to 1 plus or minus 4i. Proceeding with finding the eigenvector, we form the matrix equation 4i, negative 4, 4, negative 4i times k is equal to 0. Seeing these represent equivalent equations and dividing through by 4, we can write down that k1 is equal to I times k2. And then by letting k2 equal negative I, we get that k1 is equal to 1, and our eigenvector k is equal to 1, 0 plus 0, negative 1i. Now that we know what b1 and b2 are, we can form what's called the complementary solution, analogous to a complementary function for a differential equation. xc is equal to c1 e to the t times the column vector 1, 0 cosine of 4t minus the column vector 0, negative 1 times the sine of 4t plus c2 e to the t times 0, negative 1 cosine 4t plus 1, 0 times the sine of 4t. All we really care about with this at this point is that we don't have any terms that in our complementary solution that are redundant with our f of t. If we did, we simply wouldn't use undetermined coefficients because avoiding redundancy is more complicated in dealing with systems than it is with dealing with equations. Since we can see here that we have no redundancy with f of t, we're going to go ahead and proceed. Let's write down the form of f of t. It's 4 negative 1t plus 9 1 e to the 6t. And this is the form of a linear plus an exponential. When solving homogeneous equations, if we had a linear plus an exponential, we would have called the linear ax plus b. And the exponential, in this case, something like c e to the 6t, right? The linear needs to be generic, right? Not just ax, but ax plus b. And so here when we write down x sub p, we're going to write it down in the form of a column vector times t plus a constant column vector. For the exponential, it's a column vector times e to the 6t. Working backwards, we're going to fill in the column vector for the exponential as using a1, b1. And then the column vector of constant terms is going to be a2, b2. And the coefficient of t, that vector is going to be a3, b3. We have our proposed form of solution, and we're going to plug it into the differential equation x prime equals ax plus f. X prime is the derivative, and derivatives act the same way they would if we had just constant expressions instead of vector expressions. a3 b3 times t differentiates to the column vector a3 b3. The constant vector a2 b2 differentiates to 0. And then we're using the chain rule for e to the 6t, so my column vector is 6a1, 6b1, all times e to the 6t. ax is a bit trickier. A is 1, negative 4, 4, 1. X, I think, would be easier if we combine this into a single vector because, we're going to be multiplying here. So a3t plus a2 plus a1e to the 6t and b3t plus b2 plus b1e to the 6t. And when we multiply this, we're multiplying the entries in the top row of A, so 1, negative 4, one by one with the entries in the column of what we have on the right. It's kind of hard to see, but the entire 3-term entry in the top is one entry, and the entire 3-term entry in the bottom is one entry. So we're going to multiply 1 by that 3-term entry in the top, minus 4 times the 3-term entry in the bottom, and write it all as one big ol' entry. That's going to look like a3t plus a2 plus a1e to the 6t minus 4b3t minus 4b2 minus 4b1e to the 6t. And then we're going to take 4 and multiply it by the top entry and 1 multiply it by the bottom entry. Add them all together. The result, 4a3t plus 4a2 plus 4a1e to the 6t plus b3t plus b2 plus b1e to the 6t. I know, it's a lot. We're, remember, putting this into the equation x prime equals ax plus f. X prime we have is separated into two vectors according to form. So like a3, b3 plus 6a1, 6b1, e to the 6t. Let's go ahead and do that with the product ax. Looking across here, we have a3 minus 4b3, and then 4a3 plus b3, all those times t. Picking up all of the constant terms is going to give us a2 minus 4b2, and then 4a2 plus b2. The exponential terms give us a1 minus 4b1, and then 4a1 plus b1 times e to the 6t. And so far, all we've written down is x prime equals ax. Don't forget the f. Our f is 4t plus 9e to the 6t, negative t, plus e to the 6t. Now, I hope it's obvious what we're after are a1, b1, a2, b2, and a3, b3. In order to find them, we're going to set up equations according to like terms. We have t terms, constant terms, and exponential terms. We have 0 t terms on the left, so I'll write that as the 0 vector. And on the right, the t terms come from ax and from f. So we've got a3 minus 4b3 plus 4t, plus 4, and 4a3 plus b3 minus 1. That gives us two equations that contain a3 and b3. Solving those is going to give us that a3 is equal to 0 and b3 is equal to 1. Next, we have constant terms. On the left, we have a3 and b3. And on the right, we have a2 minus 4b2 and 4a2 plus b2. And since we know what a3 and b3 are, we can use this system now to find a2 and b2. Turns out a2 is going to be 4/17 and b2 is going to be 1/17. For the exponential terms, on the left we've got 6a1, 6b1, and on the right we have a1 minus 4b1 plus 9 and 4a1 plus b1 plus 1 from ax plus f. This system of two equations contains only a1 and b1, and from this we can get that a1 is 1 and b1 is 1. Putting it all together, we get that x is equal to x sub c plus x sub p. I have down here the complementary solution that we found before, but I want to write it in a different way for combining it in the way we need to. Inside the brackets here, we have the vector 1, 0 times cosine of 4t minus 0, negative 1 times the sine of 4t. Now, of course, that minus and the negative 1 are going to offset each other. That's going to become a plus. Multiplying the cosine into the vector 1, 0 gives us a cosine on the top and a 0 on the bottom, right? Multiplying the sine into 0, 1 is going to give us a 0 on top and then a sine on the bottom. Adding those two vectors together, and then remembering we have this e to the t, is going to give us e to the t cosine of 4t and then e to the t sine of 4t in one column. We have that multiplied by c1, but I'm going to deal with that in a slightly different way. We're going to hold off on that. In the second set of brackets, we have, as you can see, sine of 4t times 1, 0 is going to put sine of 4t in the top entry. Don't forget the e to the t. And then 0, negative 1 times cosine 4t plus 0 sine 4t is going to give us negative e to the t cosine 4t in the bottom. I'm going to write this all as one matrix and multiply it by the column matrix C1, C2. You can see because of how matrix multiplication works, that's going to give me C1 e to the t cosine 4t plus C2 e to the t sine 4t, which is exactly what we would get if we cleared all the parentheses, brackets, and wrote things down as vectors. That's our complementary function. And then the particular solution that we got from our undetermined coefficients is 0, 1 times t plus 4/17 1/17 plus 1, 1 e to the 6t. That's the entire solution. Now, I think I said that undetermined coefficients is of particularly limited use with systems. The types of functions that we can work with undetermined coefficients are the same as before. The polynomial linear constant, exponentials, sines and cosines, and sums and products. But avoiding redundancy is more complicated than it is in dealing with just equations. And, I mean, face it, this process was fairly cumbersome. So we're not going to spend a lot of time with this. And in the next few videos, we're going to see a different approach for solving homogeneous systems of linear differential equations.